So yeah, Mario and I have actually put together a video where we are showing the end-to-end standalone mode demo over Colosseum, which will include some throughput numbers as well as multi-UE support. And also that will be followed by a small demo of the CI/CD system that we are setting up here. So let me share the video. Okay, I am going to play it now. Please let me know if you cannot hear the audio. Hello, everyone. My name is Shweta Srivastav, and I lead the OpenAirInterface 5G development and testing effort at OpenAirX Labs at Northeastern University. In today's talk, I provide a presentation and demo of OAI standalone mode over Colosseum testbed and an overview and demo of the OpenAirX Labs CI setup. Here's a brief outline of this talk. I'll start with an overview of Colosseum testbed, and then we'll go on to demo OAI in end-to-end standalone mode over Colosseum. The demo will show the throughput numbers with recent enhancements that our team has made, as well as multiple UE support in OAI. I'll then talk about the CI setup for OAI we are working on here at Northeastern, and then show a quick demo of the same. Here's an overview of the Colosseum testbed. Colosseum is a massive $20 million wireless emulator testbed housed at Northeastern University. It was developed by DARPA and is funded by the National Science Foundation. Colosseum is a large-scale testbed with 128 Intel Xeon-based compute servers, each connected to a software-defined programmable radio. Colosseum has a massive channel emulator which provides real-time emulation with complex RF scenarios. Colosseum is remotely accessible and can be used by researchers around the globe. Currently, it is used by several members from the research community to run experiments in various areas, including spectrum sharing, AI in wireless, 5G, IoT, and so on. So how do we run experiments in Colosseum? All user experiments in Colosseum are run in LXC containers, as these are lightweight and yet provide some benefits of virtual machines. Colosseum provides some base Ubuntu containers. Users can use one of these containers to install the softwares and libraries they need for their experiments. They can configure the containers as needed to create their own custom containers. These containers are loaded for them on the host, or what we call SRNs, at the time of their Colosseum reservation, and then they can run their experiments. We also provide 2 pre-configured OAI containers for Colosseum users, which users can use to run their experiments with OAI, or use them as starting point to make their own customizations to the configuration or the code itself. We'll be using these containers for our demo today. And although today's session is not a hands-on session, I hope to be able to provide you with some overview, as well as some pointers to resources on how to get started with Colosseum testbed. This is the Colosseum experiments portal. This is where you can go to create a new reservation for running your experiments on Colosseum. There are 2 ways to run an experiment on Colosseum. One is via an interactive reservation, where you can log into the containers and run experiments in real time. Another is via batch jobs, where you just provide all the configuration and Colosseum automatically runs the experiment for you. So let's look at interactive reservation. So to create a new reservation, we click on this plus icon here. And here it will show you all the available SRNs. They are divided into 4 different quads. Colosseum automatically assigns you SRNs based on which ones are available and how many you need. So basically you can choose all the different configuration parameters, the time that you want to start the experiment, for how long you want to run it, how many nodes you want to reserve. And if you go here and see, you will see that the OAI 5G SA RAN and the OAI 5G CN containers are provided here. So you can choose these containers and once you provide all these details, you can click on request, and the reservation will be made, and SRNs will be allocated to you based on the availability, and then you will be able to log into the SRNs and run your experiment. This slide depicts the configuration we use to deploy OAI over Colosseum. We use 3 nodes, also called SRNs or standard radio nodes. As you can see from the block diagram, all software used by experiments on Colosseum is deployed within LXC containers on the SRNs. On SRN1, shown on the right, we deploy OAI 5G core network. OAI 5G core network functions are deployed within Docker containers, and they run on a separate Docker network. OAI core network components currently deployed include SMF, AMF, UPF, and NRF. The demo OAI interface provides a bridge into the Docker network. The G-Node B runs in an LXC container on SRN2 and connects to the core network host via Ethernet. SRN2 is connected to a USRP X310 that the G-Node B uses to communicate over the emulated wireless channel. On the left is SRN3, which is the UE host. The OAI UE runs in an LXC container on this SRN3, and it also transmits and receives via a USRP X310. For those of you in the audience who are familiar with OAI standalone mode setup, there are some small differences between a typical setup and the setup used on Colosseum. One difference is that G-Node B and UE run within LXC containers as opposed to on bare metal. Even the core network Docker containers run within an LXC container. We had to make some tweaks to the Docker Compose configuration to make this work. These tweaks are available in the Docker containers that we have made available on Colosseum. We also do not use the OAI EXTDN container here, and we transfer traffic directly from this host. Also, we run the core network and G-Node B on separate hosts or separate SRNs, as you can see here, and they communicate via this Col0 interface. And the communication between them is simply achieved by setting a route between these 2 SRNs. The RF channel between UE and G-Node B is provided by Colosseum's massive channel emulator. In our deployment, we currently emulate a simple 0 dB path loss scenario. Here I am connected to a Colosseum SRN. This SRN has the OAI 5G CN image loaded onto it, which I specified when I was making this Colosseum reservation. And this is the image that is basically the OAI 5G core network image. In this, I have already installed all the prerequisites for the core network. Also, I have downloaded the core network images from Docker Hub. So as you can see, when I run Docker images, we have the AMF, NRF, SMF, and UPF images here, as well as the MySQL that will be used for the database. We have these directories here. So the main one, which we will use for configuring and running the core network is OAI CN 5G Fed. OAI core network uses Docker Compose for deploying these containers. So we will go into the Docker Compose directory. The other file we are going to look at is the Docker Compose.yaml file. This file basically provides the configuration for all these different containers, and when these containers are run, this configuration will be copied into the container. And we did make some changes for the UPF, which is the OAISP gateway container. Basically, this by default, this container runs as a privileged container. Which is not possible in this case because the LXC container that we are running on Colosseum is not a privileged container. And it's not possible to run a privileged Docker container within an unprivileged LXC container. So to get around that, we remove the privilege for this container. And we added some additional capabilities, including these capabilities that you see here. And also these sysdetails here. By adding these, we are able to get around the need to run this as a privileged container. And another change that I also mentioned earlier was to eliminate the OAI EXTDN container. This again needs to run as a privileged container, as you can see here, which again is not possible. But since this container was only for demo purposes, we don't really need it here. So we eliminate that here. So we can now go ahead and run the core network functions. For starting them, we have the script here, core network .sh. So we will run this script, and the options that we provide it are start for starting the core network, NRF, because we are using the NRF in this case, and SP gateway U. So when I press enter, you can see that it creates this network, and then it will go ahead and start these functions. One more thing that I'm going to do is I am going to run Wireshark so I can see the messages exchanged between the core network and the GNodeB or UE. And we can see here all the messages exchanged between the different core network components. I've opened another terminal here, and here I am logged into another SRN, which will run the GNodeB. We have this image loaded here, which is basically the RAN image. So now when I run the core network, I should see these messages here. So basically GNodeB exchanges this ng setup request and response messages with the core network. And successfully connects with the core network. I have opened another terminal to another SRN here, where we will run the NRUE. For running the NRUE, we do not need a lot of changes. This is the script that is present on these containers, which we can use to run the NRUE. Before we start the UE, there is one more thing we need to do. In Colosseum, there are certain RF scenarios, and we need to run an RF scenario before we can enable any communication via the channel emulator. To run these RF scenario, we use this command, and we specify the scenario number. In case of OAI, we use the scenario 10011 because this runs at 3.62 gigahertz, which is what the default frequency is, which is used by OAI. And -C option just cycles this scenario to run over and over again. Once we start the scenario, we can now run the NRUE, and it should basically run and be able to find the GNodeB. It will start the random access procedure and the RRC setup procedure, and then it will go ahead and establish a connection with the core network. As you can see here, it sends the registration request, it performs the authentication, the capability exchange, and finally it goes ahead and establishes the PDU session with the. So I'll run iPerf to do some throughput testing. On the UV side, I am running the iPerf server, and on the core network side, I will run the iPerf client. Right now I'm running traffic at 1 Mbps. And we can see that we get a consistent bandwidth or throughput of 1 Mbps. In our experiments, we found that we are able to reach up to 8 Mbps currently, and it runs stably with this value. So I'm going to try 8 Mbps for this run, and we can see that we achieve throughput of 8 Mbps on the downlink. I will now run iPerf on the uplink. So I start the iPerf server on the core network host, and I start the iPerf client at the UE side, and I will run at 1 Mbps first. We can see that the throughput on an average is close to 1 Mbps. It fluctuates a little more on the uplink as compared to downlink. So we have been able to achieve a maximum throughput of about 3 Mbps on the uplink in Colosseum. So I'm going to try 3 Mbps now. And again, the throughput fluctuates a little on the uplink, and on an average, we get about 2.5 to 3 Mbps in every run. So I hope that gives a picture of the throughput that we can achieve with OpenAirInterface in end-to-end standalone mode. Next, we will demo multiple UE support in OpenAirInterface. Multi-UE setup and configuration is very similar to single UE configuration. I show 2 UEs on this slide, but in the demo, I'll use 6 SRNs, 4 of them running UEs, and I'll show all 4 connecting to the core network and receiving data traffic. So I have opened 3 more terminals to 3 other SRNs here. We have the core network already running here, and we were running the G-Node P. And there was one SRN where we were already running the UE. So now I can simply start the second UE, and we will be able to see the packets exchanged in Wireshark. So you can see this UE also completed the connection procedure with the core network and established a PDU session. And it should have been assigned an IP address, which is right here. Similarly, we can go ahead and start the other 2 UEs as well. And we should see them completing the control plane procedure successfully. And as you can see, this third UE completed the procedures and established a PDU session. And now I'm going to start the 4th UE. In the meantime, we can check the IP address assigned to this third UE, which is this. And then the final UE also successfully goes through the PDU session establishment. And we can check the IP address assigned to it. And all these UEs are now successfully connected. I will now try simultaneous iPerf in the downlink. So I have iPerf servers running on all the 4 UEs. And I will now start iPerf clients, which will connect to each of the UEs from the core network host and send data at 0.5 Mbps. So let's start these clients, and these should connect. And we can see that all these hosts are comfortably getting 500 kilobits per second. I will now try iPerf at 2 Mbps for each of the UEs. Since we were getting 8 Mbps on the downlink, this should be okay. And as we can see, all the UEs are getting a bandwidth of or a throughput of 2 Mbps pretty much comfortably. There's some packet loss in some places. An important part of our OAI efforts includes establishment of a CI system for OAI here at Northeastern. The framework is inspired by Eurocom CI framework and uses some parts of the existing CI scripts. The goal of having a CI setup at Northeastern is to provide more diversity of resources for OAI CI, particularly for testing SDR-based OAI NRUE in order to maintain its robustness. Once completed, this will be integrated with Eurocom's GitLab code base, and any merge request or merges to develop branch, in addition to triggering CI at Eurocom servers, will also trigger the OAX CI. In the current setup, the CI uses Colosseum testbed as the test platform to run OAI. However, this framework is easily extensible to other Power platforms owing to the cloud-native model of deployment. Power platforms make use of software containers, LXC or Docker, to deploy software for experiments. We have deployed an Ansible-based toolchain, which was developed by Xylenium Research to completely automate the process of building an OAI container, which can then be easily deployed on any Power platform. This would allow testing at scale by enabling these OAI containers to be tested on multiple platforms. This slide shows the OAI CI architecture. Looking at the high-level blocks first, this is the OAI GitLab repository, the Eurocom GitLab repository. The orange block here is our Jenkins server. It runs as an AWS instance, but closely resembles Eurocom's Jenkins configuration. This blue block here is what we refer to as the CI server. This also runs as an AWS instance and is responsible for building OAI LXC containers, deploying them on Colosseum testbed, and starting the tests. Colosseum testbed is this large dotted block to the right. The sequence of events is that a merge request to the GitLab repository will initiate a master job in the Jenkins server. The master job currently does not do much, but it simply triggers a secondary job. And the secondary job initiates the Ansible pipeline. The Ansible pipeline, as I briefly mentioned before, completely automates the process of building an OAI container and deploying it on Colosseum, also generating the test configuration based on the input XML scenario file, as well as initiating a Colosseum batch job using the configuration. Colosseum runs this complete test based on this batch job configuration, and then eventually makes the log files available in the NAS storage at the end of the test. We also have deployed an Airflow toolchain that automatically retrieves the log files from Colosseum NAS storage onto the CI server. The CI scripts on the CI server will parse and check test status and make the results available to developers via GitLab in the same fashion as is done in Eurocom CI currently. So addition of the CI would be seamless for OAI developers. Here are the actual components that we saw on the block diagram. This is the GitLab repository. For now, while we are developing and testing the CI system, we have a private fork of the OAI repository. In this repository, we have set up webhooks, which specify the path to the Jenkins job that needs to be triggered whenever there's a push event or merge request event into this repository. And as you can see, that's the path is provided is to the Colosseum CI job in Jenkins. If you look at Jenkins server here, we have two jobs defined. One is the Colosseum CI, which is the master job, and then the Col CI, which is the slave job. Colosseum CI is triggered whenever there's a merge request to GitLab, as we just saw. And then this in turn triggers this Col CI secondary job, as we saw in the block diagram. And then the Col CI job is responsible for triggering the Ansible pipeline. We can see the Ansible repository here. And then the Ansible pipeline has various functions like building OAI, pushing the image to Colosseum, pushing the configuration to Colosseum, and then checking whether the logs are available or not. One more pipeline that I talked about in the block diagram is the Airflow pipeline. And this is basically responsible for fetching the log files from Colosseum back to the CI server once the test completes. So if we look at this tag here, this basically runs periodically and checks for any completed Colosseum batch jobs. And if there are any recently completed batch jobs, it fetches the log files. I will now show a quick demo of the CI system. For that, I will trigger a CI event manually in the GitLab page. So in webhooks, if I select a push event or a merge event, then it should automatically trigger the CI event and Jenkins. So going to Jenkins now, we see that it has triggered the master job, Colosseum CI, which has in turn triggered the secondary job, the Col CI job, which is running on the CI server, as was shown in the block diagram earlier. If we go into the logs, we'll see that this is the output of the master job, and basically just prints a few variables and triggers the secondary job. And if we look at the logs of the secondary job, we see that it does a bunch of things. It initially clones the OAI repository. It fetches the correct branch and version of the code based on the input that is provided to it by GitLab. After fetching the OAI repository, it also goes ahead and fetches the Ansible repository. This is where the Ansible code resides, and it clones the Ansible repository. And it basically triggers the Ansible scripts and provides these XML files as input for the test scenarios, and then goes ahead and does a bunch of processing based on this XML files. That is all that we see here. And then eventually the Ansible pipeline will go ahead and perform various actions about collecting some information. And then eventually it will start creating a new container, an LLXC container for OAI. It does a few things which are required for Colosseum in terms of setting the SSH keys and so on. And then eventually it goes ahead and builds OAI in that container. After the build is complete, it's going to get the build logs. Since the build went fine, it creates the test configuration based on all the inputs that have been provided to it from the XML file again, and then copies that configuration to the container as well. And it'll copy some control scripts to the container, which Colosseum uses to automatically run that experiment. Once the build completes, the Ansible system automatically pushes that resulting LXC image to Colosseum. It also creates some configuration automatically based again on the XML scenario file and determines what tests to run, whether to run ping and iperf and so on, and the different parameters needed for it. And once those configuration files are created, it basically pushes those configuration files to Colosseum as well, and then it kicks off a batch job, as we will see in the Colosseum page. And then now it's waiting for the test to complete and collect the logs. If we now look at the Colosseum experiments page, especially under the batch jobs, we will see that a batch job has automatically been created by the CI system. This has been moved to active batch jobs, which means it is running now. So this test will take some time to complete, and Jenkins will wait for the test to complete and then eventually collect the logs. We can now see that this job is complete. And if we look at the get reservations tag in Airflow, we'll see that it has completed fetching the log files from the completed reservation. At the Jenkins call CI job console, we can see that it has detected that the test was complete and logs have been collected. And hence it reports success of the secondary job. We can also see that the master job is complete as well after detecting success of this call CI job, and it reports success as well. Finally, if we go back to the GitLab page and check for the pipeline status, we can see that the status of the jobs is also reported back to GitLab. This slide shows the CI status and the next steps. As we already saw in the CI demo, the steps completed include the steps 1 to 10 in the block diagram, which include triggering of Jenkins job from GitLab, building OAI LXC container using the Ansible pipeline, configuring tests based on XML scenario files, running those tests on Colosseum, and collecting logs using Airflow. What we have in progress right now is parsing of the log files and generating HTML reports based on the details in the log files. So far, we have tested the CI in no S1 mode, and the next steps include addition of end-to-end standalone mode, including the OAI core network, and then driving this into production with Eurocom's help. That concludes this presentation. On the slide, I have included some links that will be helpful in learning more about Colosseum and about deploying OAI 5G standalone mode on Colosseum. Thank you.
Hello, Cheta. I think there were a question that couldn't answer in the chat. For example, one from Preyal, it was, in order to connect 4 UEs, do we require 4 USB boards? Can we connect 4 UEs using at least, can you do that, in fact, having 4 UE with radio on Colosseum?
So yeah, in Colosseum, we connect 4 UEs using 4 USRP boards. No, we have not tried it using 1 USRP board. I do not think that is possible to just use one board to connect 4 different UEs.
Yeah. In OpenAir, it's not possible today, but I would say it's not a very large development to do. It's only to add at the end a piece of software that sum up all the IQs, but it is not existing.
Okay. I have one last question. I see that is Colosseum Cloud controlled by open source platforms such as OpenStack, Kubernetes, ONAP, or anything in order to provision, automate, or orchestrate the resource of your infrastructure? Sorry.
I'm sorry, Raphael.
It's a question that was on the chat. at 11:25 my time. So I think it's. So I don't know. So I don't think. Yeah, it's in fact. Yeah, that Mario did repeat on the chat. The last question of the chat. I don't know if you can answer or not, or maybe you should point to the documentation on Colosseum.
Yeah, so actually the slide does point to some documentation on Colosseum.
Okay.
And currently it does not use OpenStack or Kubernetes for provisioning and automating. Right now, Colosseum has its own implementation, which they call a resource manager, which they use for orchestrating these different resources on the infrastructure. So yeah, it does not use these open source platforms as of now. I think it is probably in the pipeline, as far as I know, for the long term to use Kubernetes. But yeah, I do not believe it is it is currently being used.
Okay, thank you. Anyone have a question to Shweta and the team at Northeastern? Okay, let's wrap up for today. First of all, I would like to thank all the people that help us organize this workshop. I mean, the team at University of Utah that lent us use their platform over there, and we prepare together the pipeline, and we try to work on the tutorials and stuff like that. I mean, Camille and Irfan for organizing the event. I mean, that's very shout out to Camille. I mean, she did a great work. Let's finish up. Let me just open this, and I'm gonna share this. Share my screen. Okay. So as a reward for attending this workshop, you are able to compete for a challenge. And I will not read everything because I'm tired and it's quite complex, but his idea is to, based on something I showed a little bit on the lab one extension that with a channel model, is to work on timing advance. The idea is to provide, so I think the idea is to participate. So the participation will not be just restricted to people that did attend the workshop. It will be public on the website, and we will also make some it's okay now. So it will be available to anyone. I mean, we will make some advertisement on social media and on our website. So the idea is to provide a solution for timing advance for 5G based on the Lab 1 and Lab 1 extension that we did. So that's one. And okay, let's see if I can. Yes. And there will be awards. Okay, so that's something that you need to be aware of. So here you see we have some explanation on what to do and stuff like that. So we evaluate some reference in terms of documentation, and we have put dates so for submission. So submission will be made by email. If you need more detail for the submission, just contact the workshop email address, and we'll give them more details if it's not possible. And we'll announce the award on the January 21st, depending on the number of participants. I still have to work to do in parallel. Yeah. And you can work in team up to 5 members per team. Okay. So that's it. I think that we'll wrap up our run track for today.
But the award is 1,000. It's not 5 times 1,000.
No, it's 1,000 euro per team. Okay.
Okay.
Or 700 per team or 500 per team. Okay. Sorry. Thank you very much for the clarification, Laurent. Anyway, I mean, the idea is for you guys to start being a contributor and not just a user. So have fun. Thank you very much for your time. Irfan, do you want to say a word? No, you good? Okay. Thanks a lot for the one that did attend. I mean, some guy from Indonesia or China. You guys are very courageous and brave to join us at such a time. Thank you very much for your time.
Thank you, Raphael. Thank you.
Thank you.
Okay, and if you registered, tomorrow we have the core network session and the Mosaic 5G sessions. So if you are registered, see you tomorrow. Bye-bye.